Welcome to the second video of this module. Now notice what we did in the last video was deal with the first set of rules of replacement. And in total, we're going to have 10 of these. We've covered 5, and so now we need to move on to the rest, the next 5 possible rules of replacement. And so let's just jump straight into the rules. So the first rule is simply transposition, and the abbreviation of this is just trans, or T-R-A-N-S. And essentially, transposition permits us to turn any conditional statement around. And we can derive this rule from what we know about modus ponens and modus tollens. We know that if any conditional statement is true, then if its consequent is false, its antecedent must also be false. And therefore, any conditional statement is logically equivalent to the conditional statement asserting that the negation of its consequent implies the negation of its antecedent. Now, once again, that's a mouthful, and it's much easier to understand when we look simply at examples. So here's a simple example of a conditional statement. If Bob passes a class, then he will graduate on time. And if we want to state this symbolically, we find that we get if P, then G, or P horseshoe G. Now, what transposition tells us is essentially that we can take the antecedent and consequent of this original conditional statement and reverse them so long as we negate both terms. So when I say if P, then G, this is logically equivalent to saying if not G, then not P. And of course, if we look at the actual original conditional statements, we have if Bob passes a class, then he'll graduate on time, is identical to saying if Bob does not graduate on time, then he did not pass the class. So it's a fairly straightforward rule. Transposition basically tells us that if I have a conditional statement, my antecedent and consequent can be reversed if I negate both terms, and I will produce an identical statement. So if P, then Q becomes if not Q, then not P, and vice versa. If you have the negated version of this, you can simply reverse your terms and get rid of the tildes in order to make it a logically equivalent statement. The next rule is material implication, and this is abbreviated with simply IMPL. Implication is the first part of that, and this is a rather important one. Now, to state the basic rule in very simplistic terms, this rule tells us that a horseshoe, that is a conditional statement, may be replaced with a wedge sign, that is an either-or claim, if the left-hand component is first negated. And the reverse is going to be true as well. You can replace a wedge sign with a horseshoe if I drop the tilde from the left-hand component. Material implication can be very, very useful because it's often much easier to manipulate or combine two statements if they have the same basic form. That is, if both statements are in the disjunctive form, or if both of them are in the conditional form, they're often easier to work with. When we have one of each, we can use this rule to transform one of the two into the form of the other so that they match. And this, again, will make it much easier to work with in many, many cases. So let's look at some examples of how this would work. Notice the first statement here is a disjunctive claim, and it says either Bob went to the grocery store or he went to the park. And symbolically stated, we simply get G or P. Now notice what material implication tells us is that we can take this disjunctive statement and convert it into a conditional statement if G then P, so long as we negate the first term, and in this case the antecedent there. So notice what this is telling us is that the claim either Bob went to the store or he went to the park is identical to the claim if Bob did not go to the grocery store, then he went to the park. These two are logically equivalent to one another, and so we can convert back and forth between these forms. And notice too, if we start with a conditional statement, we can go the other way around and make it a disjunctive claim. So let's look at this example. It says, if you want to drive the car, then you will need to put some gas in the tank, which again stated symbolically would just be D horseshoe G. And so what material implication tells us is that this original conditional statement can be converted into a disjunctive statement so long as we negate the original first term. In this case, the antecedent D must be negated. And so what we find here is that the claim, if you want to drive the car, then you will need to put some gas in the tank, is logically the equivalent of saying, either you do not drive the car or you will need to put some gas in the tank. So the basic pattern here is fairly straightforward. A material implication tells us essentially that if I have a conditional statement, if P then Q, I can convert that to a disjunctive proposition where I have P and Q as my two disjuncts, but the first term, the antecedent, must be negated. So if P then Q is logically identical to it's either not P or it is Q, and vice versa. If I have the claim it is either not P or it is Q, this is the same as saying if P then Q. The next rule we have is material equivalence, and we abbreviate this with simply equiv, EQ, Now, material equivalent is dealing with conditional statements, but in this case, we're dealing with a biconditional statement, or the tribar. Now, there are essentially two variants to this rule, both of which simply assert the two essential meanings of the idea of material equivalence. A material equivalence is represented by the tribar, that's those three lines, and two statements are said to be material equivalence if they both have the same truth value. Now, the first variant of the rule that we can glean from this basic definition of a material equivalence states that any material equivalence, with the tribar that is logically equivalent to asserting that they are both terms are true or that they are both false. If two statements are both true, then they must materially imply one another. And likewise, if they're both false, they must materially imply one another. So let's look at an example of this first variant of material equivalence. Notice the statement here, the car is mine if and only if I purchased it, would be diagrammed symbolically by simply putting M tribar P. Now what this rule tells us is that that kind of a statement, a biconditional statement, an if and only if statement, is equivalent to essentially taking each term and making them both true and both false and saying it must be one or the other. So essentially, if and only if P is equivalent to saying M and P or not M and not P. They're either both true or they're both false. And if we put this in terms of the original statement, notice the original biconditional statement is the car is mine if and only if I purchased it. And this is equivalent to saying the car is mine and I purchased it, or the car is not mine and I did not purchase it. Now, the second variant of the rule states that any material equivalence, that is anything we're using the tribar with, the if and only if, is logically equivalent to asserting the two terms imply one another. And we can see what this means if we just go back to the original biconditional statement we're using, which is the car is mine if and only if I purchased it. What material equivalence tells us in this case is that the claim M if and only if P is logically identical to the claim if M then P and if P then M. So the claim the car is mine if and only if I purchased it is logically identical to saying if the car is mine, then I purchased it, and if I purchased it, then the car is mine. Notice what we have here really is something that we've seen before a while ago in the class when we first started talking about propositional logic, that essentially an if-then claim is different than an only-if claim. And what we're doing essentially is combining these two rules to get essentially a biconditional statement. So a material equivalence has essentially two different variants that you need to know. Essentially, we're talking about a biconditional statement. A P if and only if Q kind of statement can be logically identical to two different variations. One variation is the top one here, which says if P then Q and if Q then P. And the other is saying P and Q or not P and not Q. The next rule we have is called exportation, and we abbreviate this with simply EXP. Exportation tells us that if one asserts that two conjoined premises are held to imply a third proposition, that this is logically equivalent to asserting that if one of those two propositions is known to be true, then the truth of the other must imply the truth of the third. Now, once again, that basic definition is a bit of a mouthful. It's much easier to understand when we go look at examples. So if we take the example, if the car runs and it has gas in the tank, we can drive to the party. We would translate this essentially into the claim in brackets, R and G, then D. Now notice what this rule tells us is that we can basically move our brackets and convert the and into an if-then claim, and these are telling us the same sort of thing. So the claim now, if the car runs and it has gas in the tank, then we can drive to the party, is logically equivalent to saying if the car runs, then if it has gas in the tank, then we can drive to the party. And of course, exportation can go the other way around. I can start with everything as conditional statements and convert it into a conjunction. So if we look at this example, it says, if Frank told you the truth, then if you are late to work again, you will be fired. So this original statement, which would translate into if T, then if L, then F, essentially would convert into if Frank told you the truth and you are late to work again, then you'll be fired. And so we can essentially move our brackets back to the other side and convert that original conditional statement into an and these are logically identical to one another. So the basic rule of exportation stated formally would look like this, where notice I have on one side P and Q, then R, and on the other, everything is conditional statements. Keep in mind what moves here is how you bracket things. If the brackets are around the and claim in a conditional statement, I can move it to the other side around the conditional statement Q, if Q then R, but I have to convert the and to an if so that if I have P and Q, then R becomes if P, then if Q, then R. Now the last of our rules, replacement rules, is going to be a tautology. We abbreviate this with simply TAUT, tout. And these are insanely obvious rules here. Now there are two variants of a tautology. Both are incredibly obvious, but they're also fairly useful. Essentially, they tell us that any statement is logically equivalent to the disjunction of itself with itself, and that any statement is logically equivalent to the conjunction of itself with itself. Now, the primary effect of this is to allow us to eliminate redundancy in disjunctions and conjunctions. And we'll see what that looks like by way of examples. So notice the basic idea of a tautology is if I have the statement B here, which stands for Bob went to the grocery store, this is logically equivalent to saying either Bob went to the grocery store or Bob went to the grocery store. These are identical terms, and one can be replaced with the other. And the same thing is fundamentally true with a conjunction. The statement Bob went to the grocery store is identical logically to saying Bob went to the grocery store and Bob went to the grocery store. And so if I have that term repeated in a conjunction or disjunction, I can simply toss out the entire disjunction and just take the letter, or vice versa. And of course, the vice versa thing here is essentially eliminating the redundancy. If I have the claim either Bob went to the grocery store or Bob went to the grocery store, I can just drop the disjunct altogether and just say Bob went to the grocery store. And the same thing is fundamentally true with our conjunction when it repeats itself like this as a tautology. So the core rule of a tautology is very simple. It tells us that the term P is logically identical to saying P or P, and the term P is logically identical to saying P and P. One can replace the other. So if I have P, I could replace that with P and P or P or P. And if I had the statement P or P is true, I can simply drop all of that and just say P must be true. So these are our new 5 rules of replacement, which we can add to the first 5 that we saw, and we can also add to all the other rules we saw that were rules of implication. We have transposition, material implication, material equivalence, exportation, and a tautology. So let's walk through a few examples of logical proofs that will now use some of these rules here. So here's the first example. So premise 1 says if A then B, premise 2 says if C then not B, and the conclusion drawn from this is if A then not C. So the first step in constructing our proof, of course, is to list and number your various premises, and then place your conclusion off to the right, divided from the last premise with a slash. Now the first step in dealing with this is actually transposition. And if you remember what transposition tells us is that we can take a conditional statement and essentially flip it around if we negate both sides. So we have in number 2 the particular statement or the conditional statement, if C then not B. And if we want to transpose this, what we have to do is say it is not B, then not C. And of course, as soon as we have this double negative, we can pretty much just get rid of it by following the rules of double negatives. Because if I have it is not B, that is the equivalent of just saying B. And so I can change this conditional statement from not B, then not C to if B, then not C. And of course, from here, the solution is actually quite simple. What we have is just a hypothetical syllogism using premise 1 and then the fourth line, which we got with our double negative. And notice what it says is if A, then B, if B, then not C, and the conclusion we're after is in fact if A, then not C, and that follows from a hypothetical syllogism. And so mixing and matching our various rules, what we've done is proved that this is a valid argument. So let's look at a second example. So the first premise in this says, if D and E are true, then F is true. The second premise says, if D is true, then F is true, then G is true. And then our conclusion we're trying to draw is if E, then G. So once again, we want to set up our proof by listing our premises and numbering them, and then putting our conclusion off to the right divided by a slash. So the first step in this is actually to take the first premise and simply swap the D and E term using the rule of commutativity. So instead of if D and E then F, we get if E and D then F. Now once those terms are switched, we can rely on the rule of exportation to simply move our brackets to the other side and convert the and to an if. So number 3 here, which says if E and D is true, then F becomes if E is true, then if D is true, then F is true. And again, at this point, what we have is a pretty simple hypothetical syllogism using the second premise and the fourth line. Those put together do in fact lead to our conclusion if E then G. And so we've actually gone and proved what we're supposed to be proving. This is a valid argument. Now, from all of these new rules, we can glean a bunch of new strategies. And let me just say about all these strategies, because we have a very long list of them, that if you understand very clearly how all of the rules, both of replacement and of implication, work, then these strategies are actually pretty commonsensical. So going through them is useful both to get you to better familiarize yourself with the actual rules, and if you know the rules, then the strategies are pretty obvious. So let's start with strategy 16. This is just adding right on top of the first 15 rules. This says material implication can be used to set up a hypothetical syllogism. So to offer an example of this, notice in this case we have it is not the case that P or Q, and it's not Q or R, and the conclusion we're trying to draw is if P then R. Well, the first step in this is to use material implication, and notice what we find from the first line, not P or R, that can convert into a simple conditional statement, which is if P then Q. And we can do that again with the second statement, which is basically identical. We have it's either not Q or R, and of course we can, using the rule of material implication, convert that into if Q then R by simply dropping the negation and then converting the or to an if then. And then, of course, from here, it's pretty simple. Between 3 and 4, we have a very obvious hypothetical syllogism. And of course, that gets us to exactly the conclusion we're after. So our conclusion is now proven. Strategy 17 tells us that exportation can be used to set up a modus ponens. In this particular example, the first premise says if P and Q are true, then R is true. And the second premise simply says P is true. And the conclusion we're trying to draw is that if Q is true, then R is true. Notice what exportation does in this case is it allows us to convert that first premise into a conditional statement of its own, and then we're in a pretty simple position to start working with modus ponens. So from if P and Q are true, then R is true, we can, using the rules of exportation, say if P is true, then if Q is true, then R is true. And at this point, we just have a modus ponens between line 3 and line 2, which affirms the antecedent of line 3, and that allows us to affirm the entire consequent, which is this conditional statement in line 4. And of course, that shows us that this is a valid argument. So notice what we've done is we've used exportation here to convert a problem into a conditional statement, and that allows us to basically build a modus ponens in this case out of it. Strategy 18 also deals with exportation, and essentially this tells us that it can also be used to set up a modus tollens, which is hardly surprising if you think about it. If the goal here is to convert it into a conditional statement, we can play with that conditional statement in both directions. Notice the example in this case starts with conditional all the way through. It says, if P is true, then if Q is true, then R is true. And then the second premise says, it is not R. So notice I'm denying on the other side, on the consequence side. That suggests I'm dealing with the modus tollens. And the conclusion we want to prove is it's not the case that P and Q are both true. And to do that in this case, we can use exportation in exactly the opposite direction to move from an entire conditional statement to a single conditional statement with the antecedent in this case being P and Q. And once we have this, it's pretty easy to see how a modus tollens is going to resolve this into the conclusion we're looking for. Between line 3 and line 2, what we have with line 2 is the negation of the consequent of the conditional statement in line 3. That's exactly what you want to see in a modus tollens. And so the conclusion we draw from that is it's not the case that it's P and Q. And notice again, we've proven that this is a valid argument. And in this instance, notice that we used exportation in the opposite direction, in this case to help us develop a modus tollens. Strategy 19 deals with addition, and this suggests that it can be used to set up a material implication. Notice this rather interesting little argument we have. The only premise we have in this case is that P is true. And the conclusion I want to try to draw from this is that if Q is true, then P must be true. Now, of course, the first step here is to find a way to insert Q into this mess. If the only term I have to work with in my premises is P, I somehow have to bring Q into it, and the only way to do that is through addition. Remember, addition tells us that if I have any term, what I can do is add any other term to it by way of a disjunction, and it'll still be a true statement. So if I take P here, I can say now, logically, that is the same as saying it's either P or it is not Q. And of course, notice what I'm trying to get is in the conclusion, if Q, then P. And so I'm going to have to flip my terms around so that I get it's either not Q or it is P. And I do that by the rule of commutativity. And it's at this point that I finally get to use the material implication here to do the work necessary to get just from the letter P to the conclusion that if Q is true, then P is true. Because if we look at the third line there, it's either not Q or it is P. Material implication says I can convert this into a conditional statement by dropping the negation on the first term and then switching the either or to an if then. And so I end up with the claim, if Q, then P. And of course, that's exactly what I'm looking for in this. It's a rather interesting example if you pay close attention to it. But what we've done here is use addition to get us to implication or material implication. And what we have is a nice valid argument. Strategy 20. Strategy 20 says transposition can be used to set up a hypothetical syllogism. So let's see how that works by way of an example. In this argument, I have if P, then Q. The second premise says if not R, then not Q. And the conclusion we're trying to draw is if P, then R. Notice that transposition will allow me to take the second premise, which is if not R, then not Q, and simply flip it around to make it if Q, then R. And if I drop the negatives and swap the terms, those are logically identical. This is what transposition tells us. And of course, from this point, it's very simple to see what's going to happen. With number 1 and number 3, we end up with a hypothetical syllogism that gives us the conclusion we're after. If the first premise says if P, then Q, and the second premise says if Q, then R, then put those together, we get the conclusion if P then R as a hypothetical syllogism. And that shows us this is a nice valid argument. It's also worth noting that we can take this same example and transpose the first premise instead of the second and also produce the same basic result. If I transpose the first premise, which is if P then Q, the result is that I get if not Q then not P, and those are logically identical. And so in this case, what we find is we get the second and third lines working together will produce a hypothetical syllogism as well. Notice the second line says, if not R, then not Q. The third says, if not Q, then not P. And so I can simply jump from that to if not R, then not P. And that, of course, is what this particular conclusion was aiming at. So this tells us it's a valid argument. And notice what I've done is I've used transposition to mess around with the order of terms in order to try to set up a hypothetical syllogism into the right form. Our next strategy, strategy 21, also deals with transposition. And in this case, instead of using it to set up a hypothetical syllogism, what we can do with it is use it to set up a constructive dilemma. So notice this particular argument starts with the premise if P then Q and if R then S. And the second premise says it's not Q or it is not S. Therefore, it is not R or it is not P. Now, if you stop and pay very close attention to this, if you think about it, what we have here is a destructive dilemma. And of course, if you remember from way back in this module, we were told that we're not going to have a rule that specifically deals with a destructive dilemma because it can be dealt with a constructive dilemma and other rules. And that's actually what we're going to see right here. So this is a destructive dilemma, and it's a valid one, as is clear if you remember the basic forms. Now notice what I have to do to this is take the first premise, and I'm going to have to transpose ultimately both of these conditional statements, and we'll do this one step at a time. So the first transposition is to take the first premise, if P then Q and if R then S, and convert it into if not Q then not P, and if R then S. And then, of course, we have to transpose the other side of this as well, so that the second conditional statement, if R then S, is transposed into if not S, then not R. And then we can put these together into a conjunction. And notice what that allows us to do. If we take the second premise here, not Q or not S, and then we look at the fourth line where both of our conditional statements are transposed, what we are allowed to do is deal with this as if it were a constructive dilemma. And of course, what we get once again is a valid argument, and we've shown this by the long process of transposing these things into a constructive dilemma. We can also use a constructive dilemma to set up a tautology as a kind of conclusion that we can then reduce to a single term. So notice in this argument, what we have is a pretty clear constructive dilemma. The first premise is if P then R and if Q then R. And the second premise says it's either P or it's Q. Now notice the conclusion we want to draw is a single letter, just R. But technically, if we apply the rule of a constructive dilemma, the conclusion we're going to get is it's either R or it is R, because each of those conditional statements has to resolve itself into a conclusion put together by way of a disjunctive statement. And so what we end up with is essentially a tautology here. It's either R or it's R. But of course, the conclusion we're after, and the one we should want to be after, is just that R is true. And so we can take line 3, it's either R or it's R, and using the rules of the tautology, just reduce it to a single claim R. And once again, we get a nice valid argument. Strategy 23 says that a material implication can also be used to set up a tautology. So notice if I have this statement, if A, then not A, and the conclusion I want to draw is not A. To get there, the first step is to follow the rules of a material implication. Remember, a material implication basically tells us that I can convert a conditional statement into an either-or claim, if what I do is negate the first term. So if the claim is if A, then not A, then what I want to say is it's either not A or it is not A. And from there, we have a simple tautology. We can reduce and basically throw away the either or in the second not A to simply say not A, and we finally reached our goal. And of course, this too is a valid argument, not surprisingly. Now, strategy 24 says a material implication can be used to set up a distribution. So notice in this case, we have if P, then Q and R, and the conclusion we want to get from this single statement is that it's either Q or it is not P. Now, to do this, the first step is to use the rule of material implication. So I have a conditional statement, and what I want to do basically is convert that to an either or claim by negating the first term, in this case the antecedent P, and then I just change the horseshoe to a wedge. So if P, then Q and R becomes it's either not P or it is Q and R. And from there, we can now distribute these terms. Because remember, what distribution allows us to do is take that first disjunct, in this case not P, and then just stick it in front of both the Q and the R with a wedge. So what we get as a logically identical statement using the rule of distribution is it is not P or it is Q, and it is not P or it is R. And from here, we can just simplify to keep messing around with this stuff. We can drop one side of this. Remember, our goal here is to get to the conclusion it is Q or not P. And what we have at this point is not P or Q. And we can just drop everything after the and following the rule of simplification. Because if line 3 in toto is true, then that first conjunct, not P or Q, must be true as well. And then all we have to do is flip our terms around using the rules of commutativity to get to the conclusion we're after. And so once again, we discover we have a nice valid argument, as logical proofs are supposed to do. So we now have all of the various rules that we will use for constructing proofs. And at this point, it is a matter of memorizing these things, getting very familiar with them, and then practicing and practicing and practicing as much as you possibly can.